Welcome back, everybody, to another Big Ideas Algebra 2 lesson. Today we're going to talk about section 5.2, which is all about graphing these radical functions and inverses that we sort of hinted at last time. So our main question is, how do we know the domain and range of a radical function? And how do you sketch what's called the inverse of a function? A radical function is any function we call f of x which contains a variable inside of the radical. So, for instance, the square root function is a radical function because it's based off of f of x equals the square root of x. We're going to start by taking a look at the parent function and then figure out how to transform it. So, as always, when we don't know exactly what a graph is going to look like, our goal is going to be, our goal is going to be to pick different x values to plug in and see what works. So let's think of some x values that we can square root. Well, it wouldn't make sense to plug in any negative numbers for x, right? I mean, the negative square root of x would give us an imaginary number, so we don't want to use those. But what are some values of x that would make the square root of x a perfect number? Maybe you first think of, 4. I mean, the square root of 4 is a number, right? If we plugged 4 in here, we would get the square root of 4, and that's just going to be 2. You might realize that some other perfect numbers might be 9, because the square root of 9 is 3, and 16, because the square root of 16 is 4. And we can go this way as well. The square root of 1, for instance, is 1, and the square root of 0 is 0. So this is a good start for us. Let's start by plotting those points and see what general shape the graph takes. So we've got our 0, 0 right here, and we've got 1, 1, and then we've got 4, 2, and then we've got 9, 3, and then I think we've got 16, 4. This is what our graph generally will look like. It starts off at 0, 0. And it curves up, but the curve gets more shallow as we go. This is a bit of a weird shape for us. It almost looks half finished. For starters, since there's no way to plug in negative x values, it just starts at 0. In fact, since it starts at 0, we can say the domain of the graph is x is greater than or equal to 0. Our x values start at 0 and can be anything above it, so x is greater than or equal to 0. That means that our range is also never going to be negative, right? Like, we're never going to be able to plug in a number here to get a negative y value. So, in other words, our range is also y is greater than or equal to 0. You might say, but Mr. Strager, couldn't I plug in a number here and get the positive and negative answers? Like, isn't the square root of 16 positive and negative 4? Well, not quite. You see, there's a distinguishing feature we need to make here. If I was to ask you, x is the square root of 9, what would you say the square root of 9 is? You would just say it's 3, right? When the square root already exists, you only get a positive answer. But what if I gave you the problem x squared equals 9? Well, then you would square root both sides in order to figure out what x is. And when you are creating a square root, in the past we mentioned, you have to put a plus or a minus. So there's a big difference between asking what's the square root of 9 and you taking the square root of 9. So that's why we get no negative y values. All right. We've come so far in this unit without having to talk about transformations. We're here once again. And like I mentioned, every unit is going to have some form of transformations. Again, these transformations are no different than what we've talked about before. This table gives a couple of examples, so we know that Vertically translating moves it up or down. You just add or subtract something to the end of your problem. Horizontal is adding or subtracting something from your x. This is more going to be review for any of us. But remember, horizontal transformations happen to just our input. So you're doing whatever you're doing to x. As for vertical transformations, those apply to everything. So it means your entire problem is getting 7 added to it, or is getting multiplied by 4 in this example. Let's flip the page and see some of these transformations in action. So, there are 4 problems on here. I'd like you to pick 2 of them to do, and I highly recommend C being one of those 2. Pause the video here, and come back, and we'll see what the answers to all of these are, and then take a look at the graphs. Pause the video now, and try them out. How'd you do? If we look at A, it's asking us to translate it up 3. We know that up is a vertical transformation, so we're going to add 3 to the end of our problem instead of just our x. What this means is, when you take your parent function, the points 0, 0, 1, 1, 4, 2, 9, 3, 16, 4, we're just moving each of those points up 3. So instead of starting at 0, 0, we're starting at 0, 3. Instead of going to 1, 1, we go to 1, 4. 4, 2? No, that becomes 4, 5. 9, 3, that's going to become 9, 6. So all we did was we took our graph and shifted it up 3 units, like so. B is very similar, but instead of moving it up 3, we're moving it to the right 3. So remember, this means that next to our x, we're subtracting 3. So we're subtracting 3 from our input because it's a horizontal transformation. Again, it means that we're just going to move all our points to the right 3. So it should look something like this. Bam. Next up for C, we have 2 transformations happening, so 2 things are going to change. It's flipped over the y-axis, so instead of looking like this, it's going to go the other direction. And then it's translated down 4. So for instance, we could flip 0, 0, but that's going to stay where it is, and then move it down 4 to get our first point. We would flip 1, 1 to be right here, so negative 1, 1, and then move it down 4. We could repeat this process with each one of our points, and if you did this, you would get something that looks like so. This graph is going to be facing the opposite direction from the other ones. We flipped it, and of course, it's also down 4. Last but not least, for problem D, we have a vertical shrink. Now remember, with horizontal stretches and shrinks, it's the opposite of this. So if it was a horizontal shrink, we would turn this 1/2 into a 2. But if it's vertical, it just means it's multiplying by 1/2. So we're multiplying all of our problem by 1/2. That means all of our y values are going to be half as tall. So instead of getting all the way up to 1, 1, we're going to get to 1, 1/2. Instead of getting to 4, 2, we get to 4, 1. And instead of getting to 9, 3, we get to 9, 1.5. It looks like the graph has been flattened by 1/2. That's because we vertically shrunk it. Perfect. Example 2 has us describe this transformation using words. So let's identify what's different about it. We've got this negative in the front. We've got this 2 next to our x. And we've got this plus 5 on the outside. So if we were reading this out in order, we could say that we started off by getting this negative in here, right? The thing that makes a negative that applies to the entire problem, not just your x, it's going to be a flip over the x-axis. So it's a reflection over the x-axis. It would basically be like if we took this graph and flipped it upside down, so it'd be going this way. A 2 next to our x tells us that it's a horizontal stretch or shrink. We have to remember, horizontal stretches and shrinks are like the opposite of vertical stretches and shrinks. So if it was a 2 being multiplied to the entire thing, that'd be a vertical stretch. Since it's a 2 being multiplied to just the x, this is a horizontal shrink by a factor of, and instead of writing 2, we write it as 1/2. Last but not least, if we're adding 5 to the end, that means that we are shifting or translating up 5. Perfect. Of course, square roots are not the only type of root we're going to see, not by a long shot. We're going to see cube roots and fourth roots and fifth roots, but usually just seeing the square root and the cube root will be enough for us to see a pattern. The first thing we notice is we want to plug in values of x that make sense again. So yeah, we could plug in maybe 0, we could plug in 1, we could plug in all these perfect cubes. But recall that perfect cubes can also be negative. So if 1's a perfect cube, that means that -1 is also a perfect cube. If 8 is a perfect cube, that means -8 is also a perfect cube. And in fact, those are what we're going to graph. -8, -1, 0, 1, 8. The cube root of 0 is 0, the cube root of 1 is 1, the cube root of -1 is -1, because -1 times itself 3 times will make -1. What times itself 3 times will make 8? Well, that's 2 times 2 times 2. So when we have x equals -8, that means y should be -2. We get a pretty good picture of what our graph should look like. We've got a dot here at 0, 0. We've got a dot here at 1, 1. We've got a dot all the way over here at 8, 2. But we also have a dot here at -1, -1, and a dot here at -8, -2. Everybody, this graph here is going to look like so. It's almost going to be like we took two root functions and put them tail to tail with each other. Like so. This function actually looks like a function we saw in the past. In fact, if I turn my paper sideways, what does this look like? It looks like a snake. It looks like the cubic function. So, let me give you an example. Let's see if we can plot x cubed on the graph right next to it. Well, let's make a table so we can plot x cubed. Again, here are x's, here are y's, and we're trying to see if we can plot g of x equals x cubed. Well, we can use these same, or at least similar x values. Like 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, -1 cubed is -1, -2 cubed is -8. Hang on a second, these are the same numbers, just flipped around. And in fact, when we start plotting these points, we start to see a pattern. 0, 0, still there. 1, 1 is still there. But 2, 8 is all the way up here. And similarly, we get -1, -1 here, but -2, -8 is down here. This graph is going to look like so. It's going to sort of peel off in this direction and peel off in this direction. This is our snake that we talked about a couple units back. Why on earth do these two look so similar? Doesn't make sense. Well, maybe it does if we knew about the concept of inverses. So, before we start talking about inverses, I want to show you what this graph will actually look like on our graphing calculator. So what I'm going to do is I'm going to graph both of these next to each other, and let's compare them. Here are graphs, and I'll zoom in a little bit so we can see it a little bit better. Here are graphs for the cube root of x And there's our graph for x cubed. They look like they're almost opposites of each other. We touched on inverses once before, but the inverse is found when you switch your x for y and your y for x. The inverse is always going to look like the opposite of its original. So let me give you an example. Let's say we had to find the inverse of these two functions, right? So f of x is the same as y, so this is like y equals 2x plus 3. To find the inverse, we just change the y into an x and the x into a y, and then solve the problem for y, getting y by itself. So how can we do that here? Well, we start by recognizing, hey, we can use reverse PEMDAS to subtract 3 from both sides. That'll give us x minus 3 equals 2y. And then divide both sides by 2 to get our answer. Our answer is x minus 3 over 2 equals y. Y is by itself. When it comes time to plot both of these on the same plane, we'll see what they look like. But I first off want to find the inverse of b. We've done this type of inverse before. This was in our last unit, Unit 7. If we try to find the inverse here, all we need to do is, again, swap our y and our x. So this is y equals 4 over x plus 2. We just need to swap it so it's x equals 4 over y plus 2. Like so. We also learned a shortcut last unit to help us with solving this. Does anyone remember? The trick we learned is, anytime you have a whole number on one side of an equal sign, and your denominator on the other, you can swap the two. So we can rewrite this as y equals, y plus 2 equals 4 over x. Y plus 2 equals 4 over x. Because all we did was we swapped this entire denominator, y plus 2, with this entire side, x. And now we can subtract 2 from both sides, giving us our answer, y equals 4 over x minus 2. Of course, we can plot these points by hand if we would like to, but I'm going to use the graphing calculator just so we can see a little bit more clearly what these inverses are going to look like. So let's start off with A. In my graphing calculator, I'm putting both of these functions down, like so. I'm going to zoom to normal so we can see it. Let's see them. There's our first one, and there's our second one. I'm a little bit zoomed in, but you get the idea. It seems like on our original, if we were graphing it, we would have points at 3, we would then go down to 1, and it's sort of like we're going down to left 1, or up to right 1. This would be what our function looks like. Our red function is almost like the opposite of that. Instead of going up to over 1 and starting at 3, we're starting all the way here at x equals 3 and going right to up 1. It's like our directions have been flipped, or if you are keeping a keen eye out, it's almost like these two are inverted. This is what it means to be an inverse. An inverse function is what you get when you graph it almost the opposite of your original. Like so. Instead of going up 2 over 1, we went right to up 1. The same thing happens even when we graph our hyperbola here, 4 over x plus 2, and 4 over x minus 2. Let me graph both of these next to each other. If I put in 4 over x plus 2, like so, and over here I put in 4 over x with a minus 2 at the end, I'm going to zoom so it's square and we can see it. Let's take a look. There's our blue, and there is our red. In fact, if I zoom in, it might be even clearer to see I said might be. There we go. And there we go. It's like they're opposites. Everybody, this is very core to the idea of inverses, and it'll help us find even more inverses without even needing to solve them. There seems to be a pattern with all these inverses. All of them have been flipped over some sort of imaginary diagonal line represented by y equals x. So here is actually example A visualized. F, our blue line, is right here, and G, our red line, is right here. You can imagine it as if we're flipping the blue line over this middle diagonal line here. So here's how you can plot the inverse of a function. Make your original, plot the line y equals x, or you can fold your paper to make the line y equals x. Then you're going to flip all of your points over this line. I'll give you an example. You see how this one is like diagonally up and to the left of the line? This one should be diagonally down and to the right of the line. See how this one is exactly one square away in this direction? This one should be one square away in the opposite direction. One tip that I will also show you is this. Even without knowing exactly where to flip across the line, you can find out based on the coordinates. So what are the coordinates of this point that I just put in black ink? It's 0, 3. What are the coordinates of its inverse point? This one's over 3 and up 0, 3, 0. You see what we did here? All we did was we changed it from 0 first, 3 second, to 3 first, 0 second. We swapped the x's and the y's. So without even looking, I can tell you that this point here is going to be 1, 5. Without even looking at the other side, the other point should be at 5, 1, because that's the opposite of 1, 5. And lo and behold, this one is over here at 5, 1. So the inverse is found either by making this diagonal line and flipping your line across it, or by just switching around your x and y values. So down below, I've given you some graphs without their equations, and I want us to plot the inverse without solving and without using our calculator. Pause the video here and try and see if you can do it. Let's take a look and see. So my first order of business is going to be to draw the line y equals x. So I'm going to use this other piece of paper as a straight edge. You can use basically anything as a straight edge, as long as you don't mind a little bit of pencil or marker getting on it. There's y equals x. Normally I plot it as a dashed line, just so we know it's not actually there, but just for right now I plot it as a solid one. Now we can start flipping points over it. So for instance, our original point is right here on the other side of this square. So our inverse point should be over here on this side of the square. Any points that are directly on the line should stay directly on the line. But like over here, you could see that the line passes through this corner of the square. The point is at this corner of that same square. So the red dot should also be one corner away from the line. And I also gave you the coordinates here, so if you want to do it by coordinates instead, you can do that as well. This point is 4, 1, so we know the inverse is going to be at 1, 4, all the way up here. You get the picture? This red line is our inverse g of x. You are also possibly going to see g of x being written as this, f to the negative 1 power of x. This is just another way of saying the inverse. So you'll see it one of two ways. Over with this parabola, we can use the same trick. We can once again use our straight edge to plot this diagonal line. I'm going to use a dashed line this time, just so we know it's not part of our answer. It's just something that's going to help us make the inverse. There we go. And from here, we just start flipping points. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. Negative 1, 2 becomes 2, negative 1. 2, 5 becomes 5, 2. And negative 2, 5 becomes 5, negative 2. It's going to be a sideways parabola. The inverse graphs are always going to be like sideways versions of their counterparts. So what gives? Why are we doing inverses? Here is the big reason. Example B. Our inverse looks a lot like the square root function, the square root of x, doesn't it? So, like, if I was to plot in my calculator, for instance, the square root of x, it's going to look pretty similar to our red line here, but not quite finished, right? So what gives? Why doesn't it look the exact same as this? Why do we only get, like, 1/2 of the graph? Well, let's think about it like this. This version has a negative portion, whereas our square root function does not. They don't look the exact same because g of x has negative y values. Square root of x doesn't. Okay, let's take a look back at the very, very first page we talked about. This here. And the question we're asking is, let's graph a second function using dashed lines, h of x, which is a transformed version of f of x. In other words, what could we use to complete this parabola? Well, we would just have to flip all the points upside down, right? So, like, get a point here, get a point here, whoops, get a point here, not there, and get a point all the way over to this side. This would complete our parabola. Right? What is this function? What is this red function here? If the blue version is the square root of x, what's the red one? And then it hits us. The red version is just a reflection over the x-axis of the blue line. In other words, if we really wanted to make a sideways parabola, if we really wanted to make this work, it wouldn't be enough to just graph the square root of x. That'll give you half. To graph a sideways parabola, to graph the inverse of a parabola, you also need to graph negative square root of x. Like this. And now it makes sense. Everybody, the inverse of squaring something is square rooting it. The inverse of a parabola is going to be a positive and negative square root. Like so. Thank you so much, everybody. That ends our notes for today. Have a fantastic rest of your day. And as always, if you have questions, feel free to ask. Take care.